Okay, so on Monday, we kind of wrap up everything related to x86 assembly. Today, we'll switch the topic to something architecture. Basically, this is what computer architects do and design as a part of our job, basically. This go beyond the scope of a typical computer system. And it actually talks about, if you think about memory, we'll talk about how it actually works. So in today, I'll give you some introduction and go into more detail going forward next week, right? So I cannot move the slides. Let's see what's going on here. Okay, so when you buy a memory, as a customer, what do you want? Can someone tell me what do you want when you buy DRAM? High number, I guess you mean high capacity, right? A lot of it cheap, right? You probably don't want to spend a lot of money on it, right? What else? So how many of you noticed there's a number after the DRAM, right? A lot of space there, exactly. I want my memory to be unlimited, basically. If I can have that, right? It's gonna be awesome. So have you heard this number after the DRAM that say something like 20? Oh, I can't. Pen, please. Okay. So something like 2033, 2666, or 3000 something, right? Have you seen that number after the DRAM model? Basically, you have say, okay, DRAM that are 8 GB. Afterward, there's this four number. How many of you seen that before? Actually, if not, I'll give you an example. So let me go to Chrome. Okay, so you see this website, right? I'm going to advise and hopefully they have DRAM for sales. And my internet seems to be really bad. All right, computer hardware DIY, right? Oh wait, memory right here. Nope, I do not mean SD card. RAM for PC. Okay, right here. So when you go buy a RAM for PC, there are these kind of thing, right? DDR3, DDR4. So you see on the left side over here, right? There's different DDR that I highlight here. The different DDR number are basically kind of like the model number. DDR2 is one technology, DDR3 is another technology, DDR4 is the newer technology. So DDR3 is newer technology than DDR2, DDR4 is another technology than DDR3. There is actually an entity that defines how they would behave. And afterward, let me zoom in. You see this number at the end, right? 2133, 24,000. Oops. The number after the model right here. You see that number? Can someone say something? Okay. So that number actually is the clock speed of DRAM. So can someone tell me, do I want a higher number or do I want a lower number? Higher in the sense that if you want to make your DRAM faster, you would want a higher number, right? So there are actually more detail into what exactly how you would read that. If you're curious, let me know. Basically, it would help a little bit when you want to go buy this stuff. You see this L letter at the end here. Anyone want to guess what does L stand for? L actually stands for low power. So on your laptop, for example, right? If you buy DRAM from for your laptop, you see that it's DDR something L. It would consume a lot less power, and uh, that's why your laptop lasts longer. If you actually do a breakdown, the main memory, this DRAM consumes so much power. It's actually a good fraction of the total power is dedicated to memory. That's why they want a lower power ones. So as you can see here, if you compare different models, so from 2400, the speed right here, right? You see that the one that has higher speed right here is costing a lot more. It costs you 22,000 baht, right? For 32 gigabyte. If I want a 32 gigabyte with the DDR4 2400, how much do I have to pay? Around 6,000 baht. So you can see that this is another thing that costs money, right? So this is what you want in the main memory. So let me erase this number. So any question about the DRAM clock speed? Basically, clock speed tells you how fast your DRAM is. So basically, what you want in memory, obviously unlimited capacity, zero latency, right? When I want my data, it would magically appear. It's a black magic that hardware designer is trying to design the hardware so that as programmer write their code, they don't have to always pay this latency. You want it for free. You don't want to spend money, right? Ideally, I don't want to spend money to buy DRAM. You want a lot of bandwidth, right? So this is basically allows you to send 10,000 different data access at the same time. This is what it means by bandwidth. How much parallel data access you can handle for the system. Uh, the problem of this conflict with each other, right? So if you want the DRAM for free, they probably suck. It probably perform really badly. It probably is small. And then fast memory consume more power, right? Parallel, having high bandwidth DRAM can be also expensive. So basically, all these desirable goal are somehow not achievable. On top of it, how many of you heard about the word virtual memory? Okay, yes and no. So for those who never heard about it, we would study what it is and what is the benefit behind virtual memory. But basically, whenever you write a program, even though when you use pointer, right, even when you use pointer, do you ever need to be worried about who else are using the other addresses? Ever? I'm asking you that question. So when you get segfault, do you have to worry about who owns that? Or do you just operate somehow you call malloc and you magically get this chunk of memory? It's the latter part, right? So you call malloc, even though you need to manage the address, this address it seems unlimited, first of all, right? You can keep mallocing at some point, hopefully as long as it doesn't take too much, then you can keep calling malloc. It's contiguous. You can malloc for say 1 gigabyte of data, right? It doesn't mean that you're gonna have this 1 gigabyte contiguous chunk of data all the time. But somehow, from your point of view, the address is contiguous. The address that you get would be from address the first byte to that 1 gigabyte. The whole thing would be contiguous, right? Doesn't mean that it physically would fit in there. We'll talk a little bit more about this when we talk about virtual memory. But basically, whatever address you see, whatever address you see when you program, including when you program in assembly, these addresses are virtual address. It is being supported by virtual memory. It gives you a lot of room to make sure your life is easy. Why is that the case? You don't have to worry about, okay, are there other programs that are using the memory right now? Can I use that address? Can I access this address? What is the physical location of that address? You don't have to worry about it. This is done by the OS and the hardware working together. Inside your hardware, DRAM, as I said earlier, is one physical thing. It's a 1D space, one-dimensional space, starting from address 0 to whatever address is that capacity of DRAM. Let's say it's 4 GB. Basically, the last address would be at that block at the 4 GB region in DRAM, right? So hopefully you understand that there are something going on in hardware and there are something going on in the OS. We'll talk about this. But let's talk about the current memory technology, right? The first thing I'm going to introduce to you right now is all the mostly textbook, so hopefully you don't get too bored yet. But the first thing that you can have on your computer, so when you buy a laptop, there are mainly two big components of memory. The first one is called SRAM. SRAM stands for Static Random Access Memory. What it does is essentially we call this a cross-couple inverter. So it looks something like this. If you draw a circuit diagram, you have an inverter, right? Can someone guess what does the inverter do? Let's say I have signal 1 coming in. What would the inverter do? Yep, it apply a NOT, right? What SRAM would do is it have another switch that connects to the address. This inverter basically it perform a NOT, and you see that it's looping, right? So it would trap the electron for infinity until I close that switch. Basically, that's what SRAM is doing. That's how they keep the electrons in the cell. Basically, you would trap the electron. Basically, when you close the switch, if you want to store a value 1, you drive the electron in. And then you open the switch. When you open the switch, you just got this loop inside, right? When you open the switch, this is what you got, the whole thing inside. Electron was just going around, and that's value 1. Otherwise, when you release the electron, you get the value 0. This thing is really fast. This thing is really fast, but it's big. Why is it big? Inverter costs 2 transistors, so 2 inverters is 4 transistors. This is 1 transistor, this is 1 transistor. So in total, how many transistors do I need to build an SRAM that can store 1 bit? 6? Yep, exactly. Basically, you need 6 transistors to build 1 SRAM cell that can store 1 bit. And then there's DRAM. You probably got sick of this word by now. DRAM is your memory that you buy. It's cheaper but slow. Why are they cheaper? How many of you seen the dash camera, like the dash cam on the car, in a car? I'm sure everyone's seen it, right? The dash cam. You might also notice that when you stop the car and turn the engine off, the dash cam power go off right away. The reason behind that is a lot of dash cam is powered by capacitor. Basically capacitor is where it's a circuit that store electrons. So instead of using this couple inverter in here in SRAM, what DRAM do is, okay, why can't I just use capacitor? I have a capacitor here, right? That this thing store electron. And you have to switch, right? How many transistors do I need for a switch? One transistor, right? One capacitor. So you only need two components. And it turns out you can make this really small. How small? Right now, these capacitors store definitely less than 10 electrons. It's that small, right? So when you read the technology news and see that, okay, these days Intel or AMD or Apple come up with a chip that uses 7 nanometer technology, 10 nanometer technology. You've heard about that word, right? Something nanometer technology. Can anyone want to guess what does that nanometer stand for? It's a size, right? It's a size of something. So if you look at this logic, what is a common circuit in there? You guys still here? Yes, some electrical circuit unit, right? And what is the most common unit here? If you look at electric related items where you can have resistor, you can have transistor, you can have capacitor, you can have conductor and things like that. The nanometer stands for how big is a transistor. Basically, if you can make transistors smaller with the same area, you can pack more transistors. So basically, depending on these technology, you can cram more bits, right? You can basically, essentially, you can put more bits. That's why DRAM grow bigger. That's why 10 years ago, you're looking at 4 gigabyte DRAM. These days, each one of those piece of DRAM would be 8 or 16 gigabyte, right? Because you can shrink the transistor. Exactly, that's actually Moore's law. Moore's law is basically telling the trend that every few years you can double how many transistors you can pack in one unit of area. And then if you read the news, the technology news, people right now are talking about the ends of Moore's law. Why is that the case? Because I can't fit electron in the transistor anymore. It's way too small. So there are new technology that people can use to store things, right? So basically, as I said earlier, SRAM is consists of two cross-coupled inverter. 4 transistors are used for storage. The other 2 as a switch to access the storage, right? DRAM, 1 transistor, 1 capacitor. The charge inside the capacitor tells whether it's a value 1 or value 0. You see the transition from programs, right? Programs to electrons and bits inside your computer. So hopefully you see that transition that, hey, somehow I have a program and this program becomes a physical thing that exists in the world. It's just electron moving around. One quick thing is that because it's a capacitor actually lose electron over time. It's just the nature of that. So DRAM cells always have to be refreshed. Unless you take an architecture class, we're not going to worry about that. We assume this is a magical thing that is done in hardware. So let's talk about trade-off, right? SRAM obviously is faster. I said earlier, it's used cross-coupled inverter. You can sense the electron right away. So you can actually read the value within less than 1 nanosecond or a few nanoseconds. So if you have 512 bytes of SRAM, it's almost as fast as register. If you have bigger SRAM, it might take a little bit more time. For DRAM, it's a lot cheaper, way cheaper. If you look at SRAM, we are talking about megabytes of SRAM. If you look at DRAM, we talk about gigabyte of DRAM. Gigabyte is 1,000 times higher than megabyte, right? So you can see now that you can have a really big storage too, but they're going to be slower. How slow? Around 40 times to 100 times slower, depending on how many CPU processors, basically how many processors want to use DRAM at the same time. This is off topic, so it won't appear on your exam. But I want to tell you, what about upcoming things that you can see in the market in the next few years, right? Just because I know these things. So if you buy fancy GPU, that came out these recent days, they actually do this thing called tiling. Basically, they put the RAM chip next to each other. You get way more bandwidth. Then you can actually put DRAM on top of each other. So if you look at those DRAM chip, the black thing from DRAM, so these this black thing that you can see here, chip that store data. Those are where the capacitor are, and it's a 2D thing, right? Basically, you store that in a 2-dimensional format. There are actually technology to actually put that chip on top of each other and somehow would retain the heat exchange and it won't burn, like literally burn into fire. It's actually a lot of these things are in development and it should be off the shelf soon. So you should be able to see a big DRAM coming out in the next, say, 2 or 3 years, I think, in my opinion. Uh, and then there's another type of DRAM that we look at terabytes of DRAM. It's not DRAM anymore because it uses a different type of devices. It's only a bit slower, but it's way bigger, right? This is called NVRAM, and there's also hybrid, which is like DRAM plus NVRAM. All these things will become a product in the really near future. So hopefully, if you ended up having to do like things like machine learning or fancy or complex big data analytics, and you say, "Hey, I need more DRAM," it's coming out. So that there are actually trends that are increasing the capacity of your DRAM, and these are the new technology. I actually have some projects related to this. If you're interested for your summer to do this as a summer project, let me know. There are a lot of things that are being active right now in terms of research. But at the end of the day, even though you have huge DRAM, it's still slow, right? This basically is limited by how fast you can move electrons. And electrons, the way it moves, is governed by law of physics. You can't break the law of physics. It's just impossible, right? So you can do things like writing fast program. And this is why these material matters. Once you know how DRAM work and how does memory access work, you can actually modify your program to make it fast. The key here is how to hide that slow memory access. And then the increasing size of data, basically these days, modern day program demand a lot of data, right? So it make optimization get harder and harder. So hopefully at the end of this class, if you say, I hate system, I hate hardware, at least these are some takeaway that you can get from the class to say, okay, if I want to write my program and want to make sure it's fast, these are things that I want to be aware of to minimize the impact of my data access. So the idea is, okay, if we want to speed up memory access and we want to be greedy, we want to get a really fast and really large memory, what do we do, right? Right now, what do we know? We have SRAM that are fast but small, right? And then we have DRAM that are big. One of the idea is, well, why don't we have multiple layers of these fast then small memory, right? Because that's what we observe. So when you buy a CPU, when you buy a computer, every single computer comes with this thing called the memory hierarchy. The memory hierarchy basically consists of really small SRAM cache. Notice the word cache, right? If you buy processor, the one of the specifications, it would tell how big is the L1 cache, L2 cache, L3 cache. L stands for level. Level 1 cache, level 2 cache, level 3 cache, last level cache, and then DRAM. So what it does is you can have this really, really small SRAM cache. If you don't have enough memory to store your data, then you spill over the additional data into the level 2 cache. If level 2 cache is still too small, then you spill over to the level 3 cache, right? Then, if it's still too small, go to DRAM. It's big, right? And this is called memory hierarchy. And this is I guess the cartoon example. What do I mean? Let's say you buy like right now, because of the space limitation, let's say it's a 3-core CPU. Usually, each of these CPU core would have its own level 1 cache that are really small. Okay, so that's a good question. So the question is, what's the difference between sub-nanosecond and nanoseconds? Sub-nanosecond basically take less than nanosecond to access. Nanoseconds is basically greater than 1 nanoseconds. And why is that important? If you look at the CPU clock, one clock cycle is around 0.3 nanosecond. So if you have a really, really small SRAM that take less than 1 nanosecond, that's only a few clock cycles. If it's more than 1 nanoseconds, it's going to the region of like 10 cycles, 5 cycles, that's longer. So to access the level 1 cache is fast, then the L2 cache is slower. L3 cache is even slower. DRAM is really slow. And I'm gonna have an analogy for that on how slow it is. But let's look at this. Basically, this is a illustration of what you get when you buy a CPU core, a processor. Let's say you buy an i5 processor. You have multiple cores, right? Each of these core would run a program. They have their own private L1 cache that are small and really fast. Then you have this shared L2 cache, or some system might even have the L3 cache that are bigger, right? And then at the end of the day, you have the main memory. So right now I introduced this concept called caching. So we're going to go into detail about caching. Any questions about the memory hierarchy? Okay, so yeah, the question is, can I explain the slide again? If you go back to our assembly code, right? Let's say I have a move instruction that has to access the data in here. So let's say this is where my data is. And this is where the move instruction is, right? Basically, when I run that, what the move instruction has to do is to go here, right? And find the data. Then how long is that going to be? Is as long as how long it takes to access one single piece of data in DRAM, right? Because as I said earlier, DRAM is slower than SRAM. So our idea here is, well, can we make this data access faster? And one idea is, if we know that we are going to access this piece of data, why don't you put the data here, right? If you can put the data here, the move instruction would just need to go to L1, right? These would take less than 1 nanosecond, but this would take like 12 to 50 nanoseconds. So going all the way to DRAM is going to be slow. Memory hierarchy allows you to put some of the data inside this cache. And they're fast. So your move instruction is now fast. Why is L2 share? So that is basically that's a design question. Basically, L2 is a little bit slower and bigger. And because they are bigger, the idea is sometime it might be okay. So let's say this is low like low memory demand program, right? And this is like high demand. What does it mean? Basically, these core use so few data that everything fit in here, right? Everything fit in the L1 cache. You can put all the data of this CPU core inside the L1 cache. If you make the L2 private, will there be any data in the L2? The answer is basically no, right? Because L1 is big enough to put everything in here. So to maximize utilization, one way is to make sure L2 is shared. Everyone can use it and is free for all. If you want more data, go ahead, you can take it. If you don't need to use L2, that's fine. I can give your allocation to someone else, your fraction of the L2 to someone else. That's why the L2 can be shared. That's a benefit of sharing, right? You basically you have a pool of resource. And if you don't need to use the resource, you can give it to someone else. If the L2 becomes private, I can't give it to someone else. That's a wasted resources. So does it answer your question? The other question is why does it have to go through the L1 cache? By technically, it doesn't always have to. This is a really good architecture question. Basically, you don't need to go to the L1 cache. And there are different trade-offs that can impact how easy to program, modification in the OS, modification in the hardware, but you get different benefits. So it doesn't have to always go through the L1 cache. So that's a great design question. And as a like when you actually design this hardware, these are open-end questions that you need to deliver for your customer. Basically, you just look at the customer demand. What are the program that I'm gonna run, right? Different program has different, I guess, affinity, how friendly they are toward each policy. So you would pick the policy. Okay. All right. So caching. Today we're gonna go into what does it mean to cache things inside this cache that happen to be on everyone's processor. So let me give a like a human-like overview, right? Because I think this is probably the easiest way to understand this topic. So let's say I want to make coffee, but I run out. I need to buy a coffee bean. Basically, I need to get a coffee bean somehow to make coffee, right? In a computer, what's inside the processor? What is the really tiny memory that you have in the computer inside the processor that we covered already on the assembly lecture? What are those? Yes, exactly. Register, right? The EAX, R9, R10, R8. Think of register as your cupboard inside the house, right? If you have coffee beans there, you can just go there and grab it and make coffee. And it's convenient. You don't have to walk anywhere, right? So what is the problem of my pantry or cupboard or whatever that store coffee bean? The space is really, really limited, right? In x86, I only have 16 register. How big is one register? 8 bytes, right? 8 bytes times 16, how big is that? 128 bytes. You can only have 128 bytes of actively computing data. That's extremely small, right? So if my coffee bean is not in the pantry or cupboard inside my house, what do I do? I guess I can go to nearby 7-Eleven, right, and see if they have coffee beans. Think of this as a cache. It's everywhere. It's close to your house, right? Basically, this cache is really close to your house or your apartment, right? And then you can go, and it's convenient enough. You don't have to walk that far, and hopefully you can find some coffee beans. But if they're not there, because 7-Eleven is still a small thing, right? So the next step is you can go to a nearby mall, right? Hopefully Lotus, Big C, Central, or whatever is the closest mall that you have coffee bean in stocks, right? And notice how the size get bigger, the size of storage, right? You can store so many things inside my cupboard. Then you can store so many things inside 7-Eleven. Then you can store so many things inside a mall, right? So think of it this way. It's easy to get to my data in the register. It's not too bad to get my data from the cache. It takes some effort to get my data from the main memory. If my data is not there, what's the next level? DRAM is memory. Basically, DRAM is inside the main memory. So if my data is not in DRAM, what is the next storage element that you buy when you build a computer? Yep, disk, right? The disk, hard drive, or SSD. Think of it as you need to go to coffee farm in Thailand to buy coffee bean. It's how inconvenient that is, right? And then if you store data in a network drive, think of like you have to fly somewhere in outside of Thailand to get that data, right? So this you see this hierarchy of, I guess, inconvenience, right? That you have to go to grab your data. Any questions about the high level overview of and also the benefit of caching? Essentially, the size of your register is way too small. And the DRAM, which is the main memory, is too slow. So we have something in the middle that's big enough and is fast enough. Right? I guess that's also why convenience store works. You can just walk a few meters and you can buy stuff, right? So let's come back and talk about how to use the cache. If you read the ISA manual in x86 assembly, you will then notice that there's no such concept as how can I manage the cache, right? You can't create a pointer to point to a cache location. What you get is virtual address, right? You get an address. A pointer in a program point to some location inside your DRAM. In fact, in modern day computer, this cache is managed automatically by the hardware. The hardware design the policy of what go into the cache. How do I figure out this data would be inside my cache versus this data should not be in my cache, right? Some address will have the data in the cache. Some address will have the data in DRAM without having the data in the cache. Why is that the case? Because cache is smaller than DRAM. You can't fit everything in DRAM inside your cache. So you need to pick. Basically, the key here is you need to pick what go into my cache. And the old caching topic or unique type of hardware like the GPU, the graphic processing units, there are software managed cache as well. But these type of cache can be complicated to program because you need to know exactly what you want to put in the cache. Basically, it's kind of like when you need to program, how many of you get annoyed by malloc, segmentation fault, double free, illegal use of pointer? What else? What are the bugs that you've seen in assignment 2? Basically, all those pointer related bugs that you've seen on assignment 2. How many of you got sick of it already? Yeah, so I can assure you that if you need to manage, okay, you got sick of since day one. Sorry. Okay. If you got sick of that already, if you need to also not just manage the memory address, but then you need to manage what go into the cache. That's another complexity that you need to manage, right? Yeah, you can see sec fault when you close my eyes. I'm also sorry about that. Traumatizing. Yep. Okay. I thought. Okay. I hope I don't traumatize more. By asking that question. But it seems to wake you guys up. So you can probably imagine if the program give you another thing you have to worry about. This can be hectic, right? So that's why cache is managed by the hardware, and this is done automatically so that you don't have to worry about it, right? So what I want you to do for now, forget about segmentation fault. After we're done with this class, later today, you have question or assignment 2. I'll be back in the office hours. Forget about those traumatizing moments. Right now, we're skipping toward the next topic that can maybe traumatize you in a different way, or if I explain it well enough, hopefully it is obvious, because basically you can follow certain steps and you get it correctly all the time. Let me go through some basic terminology. You remember the move instruction, right? Move instruction either get something from the DRAM or read something from DRAM. Basically, you either write to DRAM or read from DRAM. How big can the move instruction be? How big is my register? It's 8 bytes, right? My register is maybe for the 60, not baby, for a 64-bit architecture, that is 8 bytes. In a cache, there's another unit. We call this cache block. The reason why we have another unit is basically from the bandwidth from DRAM can be pretty big. So there's no need to stream 8 bytes at a time. You can actually stream 64 bytes at a time. So in the processor you have nowadays, this streams 64 bytes. So it means that a cache block would be right now 64 bytes for x86. The reason why I keep calling this cache block is it doesn't always have to be 64 bytes. It's just basically depending on the hardware. Some of them would be 128 bytes, some of them would be 32 bytes, depending on the hardware. Sometimes you do certain thing to save power, sometimes you do certain thing to improve performance. But one key thing is this. The cache block is bigger than one load, one memory access. And this cache block, this confused me a lot because a lot of people also use the word cache line. They are the same thing. So sometimes I might by mistake call this a cache line as well. Cache block, cache line, same thing. All right. Each cache block is mapped to some location inside my cache. So what I'm saying here is if I have data, it could be cache, right? And access to my cache is going to go to that 8 bytes chunk of my cache block. And then there are two more terminology that you might be seeing in the future, starting from now. A cache hit, it means that when I want to look up my data, let's say I have an address, the data is in the cache. that particular instance, we call this cache hit. A cache miss is when you try to look up my address and check, okay, is the data for this address in my cache or not? And the answer is, okay, it's not in my cache. Then you have to go to DRAM. That is called a cache miss. Right. So let's just do some example. Okay, yeah. So all right. So one of your friends took ComArc before, and the comments like cache hit and cache miss is the only thing you remember from ComArc. Uh, hopefully I do a better job now for this class. I never teach ComArc at MUIC before. I'm planning to push forward. Like I'll be replacing whoever teaches class so that you have proper ComArc experience. But anyway, so this is a cache block, right? 64 bytes. If my move instruction need 8 bytes, how big is 8 bytes? It's something like this, right? So I can basically divide this into 8 chunks. So I can load, which is read, or store, which is write the data into this cache line or cache block, right? Then this is inside my cache. And somewhere here is DRAM. So let's say this is address 0x000x, I don't know, 10, 0x 20, 0x 40, 0x 50, 0x 70, and 0x F0. So if I want to get the data for address 0x10, is this a cache hit? If I have a move instruction and my address is 0x10, is this a cache hit? Do I have the data for address 0x10 in here? It's right here, right? So that's a cache hit. But let's say I do another move and the move want to access 0x30. Is it a cache hit? Oh. Yep, that's a cache miss. Basically, if you want to find 0x30 in this cache, and obviously as I use this example here, it's not there. So that's a cache miss, right? The small box is one word, 8 bytes. The big block of this 64 byte, this 64 byte is cache block. This is data word. Right. Any questions so far? Because I'm gonna move on to the next topic and tell you the normal cache organization. All right, so if you want to build a cache, what are the things that you need? What's the first thing that should be in a cache? Like this is, hopefully this is not too obvious that you did not want to answer. What is the first, probably the most important thing that should go into the cache? The data, right? You need to store the data. So obviously you need to build a circuit to store the data. What else? If you need to be able to search, if you want to be able to search if your data exists or not, right? You also need to somehow store additional elements. We call this a tag. A tag, think of it as it's an ID. that you can use to search if your data is in the cache or not. Whenever you have memory access, move instruction, load instruction, store instruction, these would, if you would try to check the tag with whatever is in the cache. So the memory address would have the tag. Inside the cache, you also store the tag. If the tag match, it means the data is inside the cache. If the tag, there's no match for that tag, the data is not in the cache. Obviously, you need to store data. This is called data store. That's where data is located, and it has limited in size. When you want to search for your data, parts of the address, as I said, is used as a tag and the index. We'll go into that in the next slide. What does it mean for the index and what does it mean for the tag? Actually, the next slide is what else I in tag store. Definitely will not go into the exam, but it's kind of good to know just for the sake of completeness. Sometimes data is not valid. When you malloc for the first time, data is junk, so you should not use it. The valid bit should become 0. It's not valid. As I said, the tag is to make sure you can search the correct entry. Replacement policy bit, we'll talk about this later. It basically is designed how you would maintain data in the cache and what data should be kicked out of the cache. Dirty bit is when you have to update. When you have to update the cache, you need to also update that same address in DRAM. So this dirty bit would tell you that, okay, if I need to update, if I need to kick this data out, do I need to write to DRAM or not? We'll talk about this in detail later, not now. Right now, let's talk about the cache organization. So let's put everything together a little bit more so you can see the big picture. A cache contains multiple cache blocks, right? So let's say I have, let's say one cache block is 64 bytes, and you buy a processor that has 512 bytes of L1. How many cache blocks can I store here? You can type in the equation too if you don't want to do the division. So what do I divide what by? Yep, exactly. Okay, that's a private message. Can someone say that to everyone? What is the answer here? How many cache block can I have in my cache if my cache is 512 bytes and a cache block is 64 bytes? It's 512 divided by 64. Right? 512 divided by 64, that's 8. Yep. So there's another terminology called cache set. What is a set in mathematical term? How can you define a set? A set is essentially a collection of items, right? It's a collection of objects, right? So we all agree that the word set means that it's a collection of objects. A cache set, basically it means it's a collection of cache block, right? Each cache block will be in one of the cache set. Each memory, the memory address will be mapped in certain cache set. So I will give an example of a cache that contains 16 cache block. So if my cache block is 64 bytes and I have 16 cache block, how many bytes is my cache? If I have 16 cache block, each cache block is 64, that's 16 multiplied by 64, right? That's 1024 bytes. Is that correct? I think so, yeah. So if you have 1024 bytes of cache, each cache block is 64 bytes. And let's say there are 7 sets. this is the organization. If you say, okay, there are 7 cache sets, then set 0 would have cache block 0 and 1. Set 1 would have cache block 2 and 3. Basically, you go down like this. And you can see that if you want to look up cache block 6, it is guaranteed to be at set number 3. Right? So each cache block will belong to one cache set. It's a one-to-one mapping. Basically, a cache block belongs to only one set. You are not going to have cache block 6 at set 3 and set 5. So you see this example here, right? Any questions about this? Okay, let's do some example. Let's say I have 4 kilobyte of cache. Cache block is 32 bytes. Cache has 16 sets. How many blocks per set? All right, so that's the exercise right now. Multiply and division. I have 4 kilobytes of cache. Each cache block is 32 bytes, and I have 16 sets. How many cache blocks do I have per set? So what would be the first calculation that I have to do here? Okay, that's quick. Yep. So that is number of cache block. So the number you say is 4 multiplied by 1024, that's 4 kilobytes, right? The 4 kilobytes divided by 32, that's 128. 128 is number of cache block. Number of cache block is 128. Yep. And you know that there are 16 sets. Each cache block would be in one other set. So you do 120 cache block per set equals 128 divided by 16. Yeah, exactly. So there are 8 cache blocks inside the set. All right. Right now, I'm going to go to another example. I ban you from answering this question because you already answered. So someone else answer this question. Let's say I have 16 kilobytes of cache. And then I have each cache block is 16 bytes. And then there are I guess 16, that should be, my bad, 16 cache block per set. How many sets do you have? This is almost the same calculation as earlier by logical flow. And Thomas, I ban you from answering. So someone else, what is the number of cache blocks do I have in my cache? What's the number of cache block? Why 64? So 64 is how many sets, right? That's the answer. Yeah. So the answer is yes, 64. There are 1,000. Well, it's 16 kilobytes divided by 16. That's 1024 cash blocks in total, cash blocks. And then you have 16 cash block per set. So you do 1024 divided by 16, that's 64 sets. All right. So let's say I have, that should be the last example right now, but I hope this is getting clear for everyone. Let's say I have 8 cash block per set, and then I have 16 sets, and then cash block size is 16 bytes. What is the size of my cache? I can't write for some reason, but yeah. Oops. And then I delete. Okay, so let me get a new number. Cache block size is 16. There are number of sets is 32. And then what am I missing here? There are 16 cache block per set. What is the size of my cache? What's the size of my cache if I have 16 bytes per block, 32 sets, and 16 cache block per set? 32 kilobytes. Wait, I don't think so. Basically, this is 16 multiplied, but you multiply every number here. Yeah, you multiply every number here, you get the size of the cache. All right. So at the end of the day, I think right now you might have realized it's just a matter of playing with a few number and multiply division. It's just the wording that right now you haven't really heard of the terminology until now. So that might sound confusing. And that's why I have 3 examples, because essentially I hope these would kind of ingrain until at least the final exam. Right? You can forget about this afterward because I'm sure you can look it up. But for now, I want you all to get used to the terminology basically. We would be like this. It's probably a little bit harder because the caching part will kind of combine a bunch of stuff together. Probably would be a written exercise, like written question that I'm gonna give you 24 hours on, unless you want to code something in the cache. This would be the last assignment for the lab. Basically, for the last assignment, I'm gonna ask everyone here to write a program, and assuming that you know how caching works, I'm gonna let you all optimize your program and see who is the fastest. So you get credit for completion, and then if you can optimize your code to make it faster and faster and faster, and you get extra credit. So hopefully it's fun for the last assignment. Anyway, let's talk about cache lookup. What does lookup mean? Basically, if I have to access my data, is that in a cache or is that in DRAM? And basically what I said earlier, data in DRAM DRAM is big. So data in DRAM is the superset of the data in the cache, right? Not all data in DRAM would be in a cache. So when you look up the data, sometimes the data would not be in the cache. It's not there. So an address to actually figure out whether my data is in the cache or not, there are 2 pieces of information. The first information is index bits. These tell what is the set. Index bits tells me the set number. Remember the set earlier? It tells me whether it's in set 3, set 5, set 0, or set 100. You can use the index bits for that. The tag bits, which is another part of your address, once you find the set, it tells whether the data is there or not by comparing the tags of every single piece of data inside that set. So let's say you have an address. I'm gonna teach you how to get the index bits. First of all, your address, right? Address is this index bit is a unique byte inside your address. Inside a cache block, right? Inside a cache block is already contain multiple bytes. The tail end of your data, your address is reserved for which of these 64 bytes that I'm accessing, right? Because your address access a data word. A data word is only 8 bytes, right? Your cache block is 64 bytes, so you need to figure out which one of these 8 bytes inside the 64 byte chunk I am accessing, right? These n bits, let's say you have 64 bytes cache block. How many bits do you have to actually be able to get the unique addressable location inside the cache block? So let's say you want to be able to access each individual bytes of data. How many individual bytes are in 64 bytes? What is 64 divided by 1? 64, right? If you want to be able to access each byte, you need to have 64 different locations. So the trail end of your significant bits, assuming that you want to be able to access every single bytes in there, you need at least log of 64. What is log of 64? That's 8. Nope, 6. My bad. Brain doesn't work. Log of 64, 6. Basically, it means that the last 6 bits is reserved for that. The last 6 bits, right? So let's call that n. The next m bits are reserved for the index bits. So let's say I have 32 sets. How many bits I need to have for the index bits? What is log 2 of 32? 5. Yep. Awesome. The rest of your address are the tag bits. So this is how it would look like. I'm gonna draw it here. Right. Let's say this is your address. Let's say it's a 64-bit machine. How many bytes are in the 64-bit machine's address? 8 bytes, right? 8 bytes. How many bits do you need for the byte? Well, I'll call this byte in block. This n is right here, right? N, 6 bits. Let's say I have 32 sets. You need 5 bits, right? So the next 5 bits are m, the index bits. How many tag bits do I have? How many bits are here? I have 5 bits for the index bits. I have 6 bits for the reserve for each byte in a cache line. I use 11 bits. In total, my address has 64 bits. How many left? Yep, 64 minus 11, right? Because why? Because this whole block is 64 bits. I use 5 for the index bits. I use 6 for the bytes in block bits. So the rest, the other 53 bits are for the tag bits. Any questions so far? So N is the number of unique location that you need to identify inside the cache block. It doesn't always have to be each byte. I can say that you don't need to go into each byte. I can go every 2 bytes. Then this number will be different. M is log of number of cache set. The log of number of cache set. The rest has bits. So if you kind of remember this formula without the confusion, I think this should be pretty straightforward. Okay, so if you were to access cache block 3 in set 2, how would that look, right? If you go to set 2, what would be the bits in my index bit? What is the bit pattern that represent number 2? Right now, index bit is 5 bits, right? So what is representation of 2 in like a binary number? 0, 0, 0, 1, 0, right? Yes, exactly. Then let's say the cache, so let's say in set 2 there are 4 cache block. If you need to search cache block 3, right? There's nothing in here. Basically, what you do is you compare the tag bits of all the cache block. And once you're comparing cache block 3, you then realize that okay, the tag is the same. So that's where my data is. So let's say the byte in block bits, which is 6 bits now, is 0, 0, 0, 0, 1, 1, right? And this is the cache block that you found. Which one of these you're accessing? Yeah, so to answer your question, cache block 3 would have a unique ID. This unique ID is the tag. Basically, whenever you bring the data in, you know the address already, right? So you store the tag inside the tag store. The tag store would then be used in the future for data access that map to that set. All right. So let's talk about the most simplest form of caching. This is called direct map cache. The direct map cache means that every set have one block. That's the definition of direct map cache. Number of set equals number of cache block because each set would have one cache block. To search, you get the index bits by log of number of set. Then you compare the tag. If the tag match, then a cache hit, otherwise cache miss, right? And if it's a hit, then you return the whatever data is here that's stored in the cache. Otherwise, you go to the next level of cache, right? This is a question I'm gonna ask you later, but you can think about this question in the next lecture. I'll come back and ask this question again. Is it possible that I can access the data in a way that I get 0% cache hit rate with the direct map cache? I actually will give you the answer. That's a yes. But then the question I'm gonna have you to think about is why, right? Any question about direct map cache before we move on? This is basically a unique name that we can use when a set only contains one cache block. And we would then talk about this new terminology called set associativity, right? The main problem with the direct map cache is data access can be mapped to the same location again and again and again and again, right? Because each set contains one piece of cache block. And let's assume that every time you access, the index bit is the same. It just means that every single access go to that same cache set. But let's say the tag never match, then you never actually get a cache hit, right? So the solution to that problem is, well, what if you store more than one thing inside the set, right? Which is the earlier example that I have. You can have 2 cache blocks in the set. You can have 4 cache blocks in the set. There's nothing preventing you from, I don't know, put in like 15 cache blocks in a set or 37 cache blocks in a set, except for that's a weird number that are not divisible by 2, but that's fine, right? So basically what you have here is cache block is this one single unit, let's say, right? It's either 64 bytes, 32 bytes, 128 bytes, depending on how the hardware designer declare. A cache set, as I said, is multiple cache blocks that are inside the same tag, right? So if you have the matching index, it go into that set, and then you search the tag. Number of cache block inside this the cache set. We call this n-way set associative cache. It's a terminology again, and I'm sorry that you have to remember the terminology. Basically, let's say I have a cache, let's say a 4-way set associative cache. How many blocks do I have in that set if it's a 4-way cache? 4-way cache. How many cache blocks? Yep, 4. 8-way cache, 8. 16-way set associative cache means that inside each cache set, there are 16 cache blocks, right? This sounds good, right? Why can't I just have why can't I increase the number of n? It improves my cache utilization. The downside of 16-way over 4-way is that each time you need to look it up, you need to compare to a lot of things. You need to compare the tag, right? So it burns more power, it takes longer. There are that performance energy trade-off versus cost. The last thing that we can have here is another unique, it's the complete opposite of the direct map cache. This is called fully associative cache. Anyone want to take a guess what does fully associative cache means? You have one cache set. If you have one cache set, it means that every single cache block is in that set, right? So number of ways is number of cache block. A cache block can be placed everywhere, and you just need to exhaustively compare. You just compare the tag throughout your cache set to find if the data is there or not. Okay, so we'll do some example here before we go to the in-class exercise. That's it for this class. The rest are the example of what happened when I have a cache lookup. So I'll do the first example for you. And I'm gonna come up with everything on the fly. So correct me if I do the math wrong, right? Please check, because this is in the afternoon. I might do the math wrong. I did once already when your friend say the correct number and I say the wrong answer. So let's say you have 4 kilobyte cache, and the cache block is 32 bytes. This is byte addressable. And then there are 32 set in my cache. It's a 64-bit machine. All right. So if this is a 64-bit machine, How many bits do I have for my address? I have bit 0 until bit what? 64, right? It's a 64-bit machine. 63. Yep, exactly, 63. And thanks for correcting me. It's byte addressable, and the cache block has 32 bytes. So, what is n? What is the number of unique location that I have to be identified? Log of 32. What is log of 32? 5, right? So you need 5 bits here. So that's bit number 4. This is bit number 5. How many index bits do I need? Log of 32 again, right? It's basically log of number of set. So that's 5 bits. So that's bit 9 and bit 10. These are the tag bits. Oops. Oh my god, I can't write it. Byte addressable, sorry. Byte addressable just means that you can access each individual bytes. Which also means that your address can go into each single bytes in your cache block. Tag. I can't write the word tag. Okay. All right. So this is an example that allow you to calculate the tag bits, index bits, and the byte in block bit, right? How many cache blocks do I have here? That's 4 kilobytes, right? Divided by 32, right? What is 4 kilobytes divided by 32? 128 cache blocks, right? If you have 32 sets, it means that this is a 4-way set associative, right? Right. Why is that the case? It's 128 over 32. So let's say my address is, I would just assume some random tag bits, right? And then it ends with 10001111110. So which set am I accessing? This is bit 0, this is bit 9. Which address am I accessing right now? Which set? Where is the index bits? It's right here, right? This is my index bits. So I'm accessing address 17. I mean set 17. I'm accessing set 17. This is the byte that you are accessing. So inside that 32 bytes block, you are accessing byte, what is it? 16 plus 8 plus 4 plus 4. So that is 28. So you're accessing byte 28 inside set 17. Any questions about this example? Basically, if I give you just these information and maybe this information, you will know that I'm accessing byte 28 from set 17 if the tag match. So the other thing is you need to figure out if the tag match in the cache or not. Okay, so let's do another example. Let's say it's a 16-bit machine. 4-way associative. how many bytes do I want? Each address 4 bytes. So let's say I have 32 kilobyte cache, and this is my address. So this is my address. Okay, so can someone type me the index bits? It will take some time, but you need to figure out how many cache sets there are, and then what is the index bits here. By the way, you can talk to, just don't forget that there's a microphone option. So you can talk through the question as well if you want to do that. Don't just feel like you have to be in Discord to talk. So how many index bits do I need here? The hint is then you need to figure out how many cache blocks do I have in total, right? And you know that it's a four-way set associative cache. So once you know the number of cache block, yep, 10 to 24 blocks. If you know the number of cache block and there are 4 ways per set, which means that there are 4 blocks per set. So there are 1024 divided by 4 number of sets, right? That is, what is 1024 divided by 4? 256, yep. And then what is log up to 56? That's number of index bits. And that's when you know log of 1024 is 10 comes in handy, because you know from 1024 you divide by 2 once, you get 512, you divide by 2 again, you get 256. So you know it's from 10 to 9 to 8. And then how many bytes in block bit that I need? There are 32 bytes block and it's byte addressable, right? So you need log of 32, that's also 5 bits. So this is byte in block, right? This part, byte and block. And the next 8, 1, 2, 3, 4, 5, 7, 8. This is the index bits. What is my index bits here? One 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 zero 1111, right? That's my index bits because I know it's the next 8 bits. So what's my tag bits? Am I missing some 0 and 1s here? 5, 8. Okay, yes, I am missing one. This is the index bit. Basically, it's the next 8 bits. I draw it wrong. I need to cover 1 more bit, otherwise only 7 of them. So if my index bits is 0, 1, 1, 1, 0, 1, 1, 1, what is the tag bits? What is the remaining bits that haven't been used? . So the rest of the bits are the tag bits, essentially, right? So you compare the last 3 bits to see if your cache is there or not. Yeah. Yeah, it should be 16 minus 8 plus 5, so that's 13. Yep, it's 3 bits. Sorry, I'm trying to do math in my head, and I somehow feel like that's 5, but yeah. The last 3 bits are the tag bits. All right, so we'll do more example the next lecture because I want to spare some time for making sure you can access the server. So I would type out the example 3, 4, and 5, and then we'll use that. I'll just post the PDF on on Canvas so you can see the question. To be honest, it would be from the previous semester exam, right? Those will be the example that we'll go through the next time we meet again. And then hopefully you can use it as a good exercise for trying to figure out how do I access the cache. And then we follow up on more topic about caching. Before we leave today, as I said earlier, I want you to log into SysQ. I'm going to show you information, but let me finish recording because it has some information that I don't really want to put on YouTube. So let me stop here for now.